Hi and welcome back to another video from Coiro, and this time it's a different approach than last time. And this is the way we normally do things here at Coiro. We first start to look into the schematics and the theory of things, and then we start to look into the practical aspect of repairing things. But in this case I actually was misled and I didn't think I had a proper schematics for this unit. I did find some schematics online for the EuroPC 2 and so on, but I couldn't find the schematics for the EuroPC, and I had an old copy lying around that was a fax copy, and that was almost unreadable. But when I searched again on Google, I actually find several places where I could download these schematics, and this is really an excellent schematics, and it's really along the lines of Toshiba, not IBM standard, but almost. And this is what we are going to do today. We are going to look through the schematics and see what we have to look into when we start our fault finding process on our EuroPC. So let's get started with the schematics, or not just the schematics, it's the whole service manual. And the schematics is only a small part of that. It all seems so easy, doesn't it? All the parts here, they come apart real nice in this overview of how this is assembled. But we knew from our last video that it actually was a lot of struggle to get this lid off. We did it the right way. As you can see, there is no screw that's actually holding this together. You can see just one screw that's approaching this, and this is the screw that's numbered with 10 down here. It's something I didn't notice when I took this apart, so I don't know if it's there. The other screws that you have around here is to fasten the floppy drive. But there's no surprises here, and they have even marked the dreaded battery that killed our unit. So this is a nice overview, and this is also the overview you use to order spare parts if there is something that is broken, because every one of these will have a parts number somewhere. But when it comes to fault finding old electronics, this is what we are really looking for. And this is not the schematics, this is just a block diagram of how the different parts are connected together. Since this is a PC, most of this is known to us from before, because every PC has a block diagram that looks something like this. You have some peculiarities here. You have the hard drive controller here. You have the special keyboard controller that drives the keyboard matrix. This is normally inside the keyboard on a normal computer. You do have what they call the CPU controller, what we today call the chipset, and otherwise it's just TTL logic on all these buffers and multiplexers. You have the RAM here. This is 512 RAM, and there is no other options for expansion of memory. And you have here the address decoding and buffering and stuff, and that's a PAL chip that does that. And you can also see here you have the EEPROM for the BIOS, and you have the CPU. And you have all the different buses, and they have divided this as coarse as you can on a PC. They have the address bus, the data bus, and the control signal bus. But all in all, this tells us what parts actually is available on this computer. And as I said, all this up here is quite normal on every PC motherboard. You can't make a PC without these parts. So that's the one that we need to get to function in our EuroPC. And since this is an integrated unit, you do have some more logic in this motherboard. You do have a floppy controller. You have the video or CGA card that's down here. You do have the real-time clock. That was the chip that was really corroded, and it's connected to this dreaded battery here. And you do have the serial controller, parallel controller, and a special ASIC that they have called the Gameship. And it's joystick, EO, and mouse port. And this is the dedicated 9-pin port that's on the back of the unit that has some proprietary signals on it. We will not look into that at least now. And this is connected, as you see, to the serial port, the mouse, the parallel port, floppy drive connector, and the RGB out connector. And you see there is a lot of TTL logic also, and all this TTL logic is normal standard types. That's quite easy to check if they work or not. And some other valuable information here is actually these crystals that's lined up here, because a crystal you can check with your scope or frequency counter or by some other means. If you have a logic probe, you can see if they are pulsing. And this we have to measure to see if things are running. Because if this crystals does not give some oscillation, you know that part of the system is down or dead. And here we go to the bare schematics of things. And here you can see the TTL logic in action. And this writing here is not something I have done. This is on the schematics that's available on the internet. And it looks like most of these schematics has a common source, because I have not been able to find one without this writing. So the earliest ancestor to these schematics probably is from some service course, some classroom action or something, because there are some descriptions here that's not normally done if you know what you're doing. So this is kind of a beginner's notes that's made on this. But here several logic chips are described. To the data latch for the memory, they actually use the F series of logic. Almost everything else is LS kind of 74 logic. Here they have the CPU and all the signals around the CPU, a very nice description. And they have the EEPROM down here. And this is the address latch. You know, on the 8088 there is a common data and address bus, and then you have to latch the addresses to get a complete address before you put it on the address bus. And the same with the data bus, and that's what you see up here. And this chipset here that is used, the FA2010A, if I'm not mistaken, I think this is the same chipset that's used on a lot of old Commodore computers, and also on some of the kits that's available on the internet to build your own XT clone. And this was a chipset that was quite common back in the day, and it actually was manufactured, I think, by a company called Faraday, and also by Western Design Center, I think. I might be wrong on this, but I seem to remember that that was the case. And here you have some auxiliary information that's very useful to us, and that's actually the CPU clock generator up here. And you have some signal that's described in megahertz, and that's very good way to start measuring if things are ticking or not. And I also made some notes already here that this is the address and data bus, and this is the address bus, and you have the reset signals and so on, and everything is marked here. And this makes it quite easy to do fault finding. And we also have a good schematics and a good pinout to actually take us one step further, and that is because our motherboard was heavily corroded, and there probably are some vias that is not working. And the best way to measure this is actually to know here that you have pin 63 should be connected to pin 2 on the LS244, and you don't have to follow that on the PCB at all. You can just measure with your continuity test on your multimeter from 63 to pin 2, and if that works, you just cross it out on your schematics, and that's okay. So this kind of schematics makes it very easy to trace traces on a PCB that's not known to you. And this is the memory ROS decoding address multiplexers, and this is done by LS158 logic. So this is quite similar actually to what's done on the C64, where they use a similar scheme to do the ROS decoding. And they also use some F series logic on the NAND gate. The F00 that stands down there, that's a 74F00. That's a NAND gate, quadruple NAND gate. Everything is nice and labeled, easy to follow from page to page. This is the RAM setup, and as you can see, this is also quite normal run-of-the-mill way of doing things, and the memory chips that's used is some variant of the 41256 chip. It's easy to follow these two to see if anything is wrong, but if there has been something wrong that broken with the memory, I don't think that would bother us much on this part of the fault finding, because if there is a trace that's broken, it will only mean that there is a memory chip that's not counting up, or that bit is not available to us. That we will be able to see on the diagnostic cards, I think. And you can also see something strange here, They state that this is 100 nanoseconds, but they have actually wrote this out and said 120 nanoseconds instead. I do know that this computer runs on 10 MHz, and I do think that for getting 0 wait states on this is good to have as fast chips as possible, and 100 nanoseconds I think is within the limit, but I do think 120 is about to push it a bit. This is the Gameship, a special ASIC made for this computer or maybe for a group of computers. I'm not going to look into this. I don't have a joystick that fits this. I don't have a mouse that fits this. So I don't know any way to actually test this chip if it's working or not. And there is one thing that is important with this chip, and is that it's connected to the reset signals. So you have reset here and you have something that they call V-reset here. And you also have the mon call here. That's probably some signals to tell the video chip if it's a monochrome or color. And you can see here that this arrow is pointing outwards down here. And that usually means that the signal is going out from this chip. And the same with the reset here. This is going into the chip. And they also say that there should be a 500 Hz signal on this, on the mono clock. I'm not sure what that is about, but probably this is signals that goes to the video controller chip. And you also have some more of this down here. You also have some IRQ outputs here, and you have some more thing that's marked with reset and stuff down here. This is the floppy drive controller, and this is the not Western Digital, it's a Western Design Center, I think. 37C65 chip. It's not a one that I've done a lot of fault finding on, but I've seen it used in a lot of computers from this area. I do think that even though this does not work, it won't be a hindrance for the system to start. So I don't think this is where we will find most fault, but as this is a PLC package that's soldered direct to the motherboard, if there are some shorts on stuff here, it will of course keep the bus loaded. And this is the hard drive interface, and the hard drive on this is connected straight to the data, address and control bus, and that means that this is kind of 8-bit IDE. And I don't have any running drive for 8-bit IDE. All my drives that I have for this kind of interface has actually stopped working, and quite some time ago too, because this was only a drive interface that was available for a very short time, and the 16-bit IDE took over quite fast. So I'm not sure if there is a way to connect with interface or something, a normal drive. But there probably is, because you can latch the signals and put out 2 bits and so on. But that probably is better solved with an XT IDE adapter connected to the XT ISA-bus. So this is also something that I think we can remove these chips and the computer will work without them. The serial interface is a standard 8250 serial interface, and this is the unbuffered version that doesn't run on much speed. You have the 82650 and so on that actually was the faster variant with the 16-bit buffer or something built in. I don't think we have to look into this, at least not at first, because I don't think this will keep the system from not working. The same with the parallel interface. This is also a standard chip on this, and it's nothing here that can make the system work. Of course, if there are some control signals or data or address signal that keeps down because there is a short in one of these chips, that changes everything. We have to desolder the chip, then we can try again. The real-time clock I only think is important for keeping track of the time, but this is a chip I think we can just take it out of the system to see, and this was one of the chips that was heavily corroded, and I've done some tracing of some of the lines around there and it seems to be okay, but of course our battery was connected up here, and we do have the time of day clock here with the 32760 kilohertz crystal. And this chip is actually a chip that is possible to get even today, both as new old stock and as desoldered parts, I think. As you might have noticed, this time I'm using my Wacom drawing board to make the comments in my video section. Please make a note below if you think the old way of using just static PowerPoints and mouse pointer is better. But now we have come to the video controller, and this is a PVC4 video controller, and this is a Paradise chip, or it was used in the card with the naming Paradise, but I'm not sure where the origin of all these chips are, but there are some generations of these, PVC2, PVC3, PVC4, and PVC4 is the exact same chip that was used in the Commodore PC-10-3 and PC-20-3. And I also seen this on some standalone ESA 8-bit cards back in the day. And I've checked the schematics for the Commodore PC-10, and the use of this chip and the wiring and stuff is almost exactly the same. And how this is interfaced with the bus and so on. So this probably is from some application example from the manual. But what we have to take into consideration when we do fault finding on this is actually the data and address decoding, of course. But you also have a memory connected to this, and you have an EEPROM connected. You have various clocks and other stuff that you need to consider. And these clocks vary with the video mode. So if you have monochrome video mode, you have some 18 kilohertz frequency. If you have CGA, you have the common 15.750 something. That's variations that we have to take into account if we find some signal here to measure at all. But this is the interfacing to the EEPROM. And you have the signal here that comes in from the Gameship, and this is mono something called down here. That might be a control signal that turns the chip into mono or CGA mode, and that means that the Gameship is responsible for that. We have the V reset that also come from the Gameship, and probably some more signal that comes this way. And you have the reset in here that we have to check so that we know that this chip is not permanently reset or something and don't wake up. And here too, all the pinouts and everything is described, but I have not been able to dig up a data sheet for the PVC4 chip. And that leads me into something that's totally lacking in this service manual, and it's also lacking in the Commodore PC 10 and 20-3 manuals, and that's timing diagrams. There is no pictures and nothing that tells me how the different timings of the buses, timings of control signals, and other stuff, how that is supposed to work. And of course, this is an area where things are getting more integrated, and you don't change individual components in the same fashion that you did with earlier generations of microcomputers. But I feel that there is something missing here, and the value of this service manual would have been much, much greater if they supplied some timing diagrams. But of course, you can go into some of the original PC documentation and find timing diagrams and use them, but of course some of these timings and some of these things is inside the 2010 chipset. And here you see how the video memory is connected, and these chips is actually the same memory chips that's used on the Commodore 64s with two memory chips. It's a 4-bit chip with the 64-bit depth. You also have the character ROM and the interfacing of this down here, and this character ROM can either be a 2764 or a 2728. But the difference between this is that the 128, they address the high bit with the jumper. That means that you can have two different character sets embedded in this ROM chip and choose which one of them to use. So that's described down here. And you do have the interfacing here to the external pinout for the monitor. And you do have something here that's marked with 500 Hertz. I don't know what that actually are. I have to see on that. And you have some set here for wait states, and that probably is either to the ISOBUS or to the memory. I'm not sure what this really is. And here we come to the keyboard controller. And the keyboard controller is a custom device for this computer, and it's a 6805 one-time programmable controller. And this is the microcontroller I have used in different projects back in the day, or some variants of this family of microcontrollers. And of course it's possible to reverse engineer this, and I got a comment that points to a site I couldn't find that say that someone has already reversed engineered this. But what we have to take into account here is that over here you do have the clock signals that goes into the FE 2010 chipset, and this is ordinary keyboard signals, so it's possible to connect a normal AT or PS2 keyboard to this point of the circuit and have input into the system. So what we do have to consider is that there are some other control signals probably that brings from this chip that might have the computer not starting or something, but otherwise this chip should not be necessary to start the computer. We might have to do something about this reset line over here, because this reset here controls something, and I don't think it's just this chip. And as you can see, the reset signal goes out down here. Hardware reset they call it, and it goes like so out of this chip. And this is drawing the reset signal low by this BC337B transistor here. So we have to look into the reset signal, and we have to measure that the system is not always reset by this, but we can fake this reset to make it appear and disconnected afterwards when we start our fault finding. And here we just see some of the pinouts for the external sockets. You have the parallel port, you have the internal and external floppy drive, and this has a kind of special connector because it's not the normal 30-something pinout. It's a 26-pin floppy connector, and that we have seen before. It's used in some Toshibas, it's used in some other computers back in the day. It's not very difficult to make adapter cables for floppy cables because all the signals are normally named the same on every one of them. And you have the external hard drive connector, and this is, as we said, some predecessor to the IDE standard. We do think that this is an X, what they called it, XOD or something. I don't remember what that standard is called, but it's essentially a 8-bit IDE. And you have the monitor, and you have the serial port. Run of the mill, nothing unusual about those two. We have the power input that we really could have gotten used for in the first part of this video when we was on our wild goose chase with the power supply. So that's good to have that documented. You have the joystick mouse port something that we don't have any device to plug into. It's not similar to anything else that I have seen. It has many of the same signals as an Atari Commodore joystick port, but it is not on the same pinout at least. And you do have here a ESA XT connection expansion port. And you have how the power switch is connected, and that's of course in connection with this up here. And now we're closing in on the end of this schematics. This part here is not really very useful to anyone. It shows where the different capacitors, and it's almost always decoupling capacitors that's in this kind of schematics. And you do have the spare gates, so if we find some use for an serial port driver or an inverter, two inverters here actually, we do have them as spares somewhere in the system. This is also quite useful when you have a computer with broken traces, and that is that you can actually pick out the traces from this diagram. And you have the battery area here where there are some heavy corrosion, and you do have the area down here where we had the keyboard controller and the keyboard socket where we had some corrosion. So this can be valuable and make you at least cross out the vias and stuff you have checked. You do have the reverse side of this PCB too, and it's of course printed as a mirror image so that you can lay them on top of each other. And you also have a list of all the spare parts, and here I mean all the spare parts. Even though it's not user replaceable, they do have a numbering of all the spare parts used here, and they also tell us something what they are. Of course, it's not of any use to us to know that this is a Gameship, as it's not possible to to get a new one. But it do list all the other chips, and yeah, I'm not sure what use this will be, because you have a PAL chip here, but you don't have the programming mask. You have the 6802 here, but you don't have the programming mask for that either. It do list that this is a 64K EEPROM. That could be of some use. It does list that the different 245s are F or normal LS variants. Yeah, and it also lists what should be in which position, and that's great when you have the soldered things. They do list some D-sub options for external floppy drives, could be useful, and I don't know what this means, because this D-sub is not a D-sub, the internal pinout for the floppy drive, so that I don't know anything about. It also states some of the other passive parts here, which diodes to expect, all the crystals, all the resistor networks, the sockets used. So all in all, it's a useful service manual. It will give us a good head start. We might be able to find the fault with the help of the schematics. We can measure out where the vias or other stuff have broken connections. We can use them to trace out various signals, clock frequencies, and buses and other stuff with the help of the schematics. We do need some additional data sheet to trace out some of the chips, and as I stated earlier, we do lack all the timing diagrams that should have gone into a schematic section of a service manual like this one. And this is as far as I'm going to go in this episode. I hope that there will be a follow episode next week when I try out some of the informations that I've given you in this video and apply them on the Schneider computer to see if we can get some life into the motherboard. So, hope you enjoyed the context. Please hit like and subscribe, it will really help out the channel. And thanks for watching, and hope to see you in the next one.